Welcome to this lecture series in linear algebra. Now that we have finished our discussion on permutations, we can define the notion of determinant on an arbitrary Fn, where f is any field and n is any positive integer. Previously, we have defined the notion of determinant for f2, where f is just any arbitrary field. We motivated this definition via the notion of area and volume in R2 and R3. So the determinant function is supposed to be abstracting out the properties that the area of a certain thing satisfies. So the determinant of a pair of vectors u and v in f2, if you think of f as the set of real numbers, is supposed to be the area of the parallelogram that you get when you complete this figure. So that is what motivated these three axioms. First is that determinant is bilinear. We made a diagram like this and justified it. This is 0 because the determinant of a thin line is 0. And this is 1 because this is a natural normalization. And we saw that under these three axioms, actually there is only one determinant function over f2, and that is what we wrote down. So this is the formula for the determinant. So yeah, the determinant is supposed to be a signed area. So when it comes to the field of real numbers, the determinant can be positive or negative or 0. So the determinant is signed area. For an arbitrary field, of course, there is no notion of sign as such. But anyway, so recall our discussion on sign of a permutation. That will be important for this discussion. And I don't want to repeat anything here. You can go back to the lectures as needed, if needed. Okay, so we will define the determinant on an arbitrary Fn over an arbitrary Fn, fix a field f, and then the determinant function over Fn is defined as a function with this grisly thing as the domain. So it consumes n vectors in an order out of Fn. So Fn is a vector space. You feed n vectors from it to the determinant, and the ordering is important. And it will output a field element, just like for the case n equals 2, it will output a field element with three axioms which are natural extensions of the previous one. The first is multilinearity, which says what? Which says that once you hold fixed all but one coordinate, and I shouldn't really say coordinate because that can get confusing. Once you hold fixed the entries in all but one slot. So suppose I fix the values here. So v1 up to vi minus 1 and vi plus 1 up to vn. These are some chosen vectors. Any arbitrarily chosen vectors in Fn. Then we get a map from Fn to F. What is this map? You pick an element of Fn, you just put it here, and now this element is an element of the field f, because this is nothing but you're feeding these n vectors to the determinant map. So when you hold fixed all but one slots, then you get a map from Fn to F, and this better be a linear map. So that is what is the definition of multilinearity. Is linear, and I'm not writing a lot of things because what I'm trying to say is that you choose an I, basically you choose a slot which you will allow to have variable entries, and then you fix all the other slots however you want. What you will get is a linear map. That is multilinearity. Note that bilinearity is just multilinearity when n equals 2. And multilinear algebra, which we will not discuss in this lecture series at all, is a very important extension of linear algebra. It is really, really very, very powerful and interesting and important. But anyway, that is for some other lecture series. So the other thing is that determinant of these n vectors would be 0 if two of them are equal. So if you can find two indices different for which the entries are the same, like if vi equals vj for some I not equal to j, then the determinant is 0. This is a natural extension of what we saw in n equals 2 case. And try to justify this in your head when n equals 3 and the field is real numbers. What happens if v1, v1 and v2 are chosen? Suppose, or let me maybe change notation. So suppose u, v. We want to find determinant of this where u is a vector in R3, u is a vector in R3 and v is a vector in R3. So the first two slots take the same value. What this is supposed to be is the volume of the parallelepiped spanned by u and v. But the parallelepiped spanned by u and v is just a parallelogram, and a two-dimensional object in a three-dimensional space cannot have positive volume, so its volume is 0. So that's basically, I mean, this is justifiable intuitively also, is all I'm saying. Okay, and a consequence of this is that, and it's very important, that the determinant of this thing is minus determinant for all vectors v1 up to vn and all transpositions tau in the group Sn or SimN. I mean, I shouldn't really call it a group because we did not use that terminology. So Sn is the set of all bijections, all permutations of this set, basically. And we define transpositions. Transpositions are those permutations which are two cycles, which flip or switch the position of two things. So if tau is a transposition, there will be some I and j distinct such that Vj will take the place of Vi and Vi will take the place of Vj. So using this, you can prove this, and if you are fumbling, then you can go to the lecture on n equals to 2 and you'll see how to do that. It's very simple. And finally, we have a normalization axiom that the determinant of E1 up to En, these are standard basis vectors, that is equal to 1. Okay. Alright, so it's a natural extension of the definition that we saw for n equals 2. And now let us proceed. So this first observation, we already made this observation actually. This thing we just commented on. Fix any positive integer, fix any transposition over this set, and fix n vectors in Fn. Then the determinant of the sequence of vectors permuted via tau, so this is sequence of vectors permuted via tau, is minus times the determinant of the original sequence of vectors. So this is what we just commented on in the previous slide. Okay. This has a corollary that if sigma is some permutation, so n is a positive integer, sigma is just any arbitrary permutation now, not a transposition necessarily, and you have n arbitrary vectors in Fn, then the determinant of the vectors permuted via sigma is the sine of sigma times the determinant of the original sequence of vectors. And this is a consequence of the previous one, along with the fact that every sigma can be written as a composition of transpositions, and the number of transpositions that you see decide the sign of sigma. So, to give some more details on what I just said, just write sigma as composition of some transpositions. Then what is sine of sigma? Sine of sigma is minus 1 to the power k. That's what we saw in our discussion on permutations. And now inductively apply the previous one. So this sigma is tau 1 up to tau k. In every step of the induction, pull out one tau, so to say, and you will be able to justify this. So please make sure you get this. And now finally, we have, I mean, this is a corollary of what we just said. N is a positive integer, sigma is any arbitrary permutation, then the determinant of the standard basis vectors permuted via sigma is the sine of sigma times determinant of the standard basis vectors in the standard order, and that is 1. So this is just sine of sigma. Okay, so very simple consequence of this particular corollary. And finally, we want to write down a formula for the determinant. So we want to say that we have some positive integer, let's say n, then and choose n vectors over fn. F is some arbitrary field, fixed. And suppose we write down each vector in its standard basis representation. So every vector can be written as a linear combination of this standard basis, or any basis for that matter. So write down vi in the according to the standard basis, and let's say these are the coefficients. Note that this may be a little bit disturbing to you. Usually we write I comma j, but I've deliberately wrote j comma I, and even in textbooks they would write I comma j. There is a reason why I'm doing it. It's not that I'm doing anything wrong or anything particularly exotic. You'll see why I have chosen this particular way of writing things in the next lecture. Anyway, so let's say vi is this sum, and the determinant of v1 up to vn, of course, we should be able to express that in terms of just these coefficients. And indeed, it is the sum over all permutations. You multiply with the sign of the permutation and write down this grisly product. So I'll let you parse this for yourself. And first, verify this formula for n equals 2. Verify for n equals 2. What does this say? And also write down this formula. Write down explicitly for n equals 3. And once you do that, you should already understand why this formula is true. But if you don't, for some reason, then let me at least offer some explanation. So what we are doing is the following. We have the first slot of the determinant function is that, and dot dot dot, the nth slot is this element. Right? Now, by multilinearity, you should be able to see that this is nothing but a sum of a bunch of things. What things? You choose one element from the first slot. So in the first slot, there are n elements or n summands. You choose one summand from the first slot, you choose one summand from the second slot, you choose one summand from the third, and so on, and up until the nth slot. And once you've chosen those summands, you just write the determinant of those summands summed over an appropriate thing. Summed over all choices of summands. So there are n choices of the first one, n choices for the second one, and so on. So there are n to the n choices. So you will write a summation involving n to the n choices, but note that whenever you choose two summands which correspond to the same j, so suppose you choose the first summand in the first slot and also the first summand in any other slot, that particular term gives you a 0, because the determinant function outputs a 0 whenever you have the same vector appearing in two different slots. Right? If this is hard to follow in this generality for n, just try to parse what I'm saying for a particular example. Let's say n equals 2 or n equals 3. So that's the thing. So a formal proof is here. The determinant of v1 up to vn is the determinant of this. Nothing has been written so far. Only the expressions of v1 up to vn have been recorded. And I have deliberately color-coded the basis vectors for easy visual perception. So you will choose, so this f, so even before I get there, what is this notation? This is the set of all maps from this set to itself. Alright? So f is what? F is a choice of which term or which summand you're choosing from the first slot, that is f of 1, which one are you choosing from the second slot, that is f of 2, and so on. So summation over all such functions, if you choose, let me maybe write one step here, so it will be easier to follow if I do that. So sum over, maybe it's a good idea to copy this, over what? Here you'll write determinant of x fi, I EFI. Sorry, this should be a 1. F1, 1 EF1 dot 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 x f n comma n e e fn. Right? You chose the f1th summand from the first slot up to dot 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 fnth summand from the nth slot. And by multilinearity again, you can pull out these field elements, and that is what this becomes. When you pull out all of them, they become a product, and this is that product. And you're left with the determinant of that guy. But note that this is 0 whenever f is not injective. If f is not injective, f takes two different things to the same value, and therefore there will be a repetition of two vectors, or I should say the repetition of one vector at least 2 times. So therefore this will be 0 whenever f is not injective, which is equivalent to saying that whenever f is not a permutation, because injective elements in this set are exactly the same as permutations. Injectivity of a function automatically implies surjectivity of the function because these two sets are the same. Okay, so this is 0 whenever f is not a permutation, so we may only vary over permutations now because all the other terms are 0. The summation over all the permutations of 1 up to n, this becomes that, and this becomes that. And now, as we already saw, the determinant of this is sine of sigma, and this term comes here, and that's it. So that's a formal proof, and you should be able to follow this. At the same time, I want to mention that we will not be using this formula too often. This is useful for computing the determinant of any given matrix. Suppose I give you a matrix, let's say 3 cross 3 matrix, and it has some grisly entries, some concrete numbers. Then this formula immediately gives you the determinant. By immediately, I mean after a lot of effort. But in order to prove things about the determinant function, even though this formula can be used, this is going to be very inelegant and will only make things opaque. We will take the softer route, we will take the more mature mathematical route to establish theorems about the determinant. One such theorem, for example, is that the determinant of any endomorphism, which we will define later, what is meant by determinant of an endomorphism, is same as the determinant of the transpose of the endomorphism. So such things will be proven via softer and more theoretically deep approach, not via this computational approach, even though that is possible. Alright, so this is all that I wanted to say, and with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.